title of the demonstration we're going to do today is called Electromagnetic Induction. During this demonstration, we're going to look at the circumstances under which changing magnetic fields leads to induced currents. We're going to use Faraday and Lenz's law to see how change in magnetic field would induce current and vice versa. So this is some background information for this demonstration. In 1831, Faraday attempted to prove that electricity could be generated from magnetism. In an experiment, he connected a coil of wire with a galvanometer and inserted a magnetic bar inside and outside the coil. What he observed was that electromagnetic induction generates electrical current. And as you can see by this equation, which is called the Lenz and Faraday's, which is both Lenz and Faraday's equation, Faraday said that the change in magnetic flux generates current, and the negative sign was later added to this equation by Lenz, who said that the current opposes the change in magnetic flux. In this setup, we have a coil of wire attached to a galvanometer. Now we can introduce a magnetic flux by taking a magnetic bar and moving it inside the coil of wire. As you can see, this generates current. Now, if you move the bar faster, you can see that it generates a larger amount of current. Another thing you can change is the amount of turns on the coil, which is represented by N on that equation. And N is directly proportional to the amount of current generated. So if you increase the number of turns of coil of wire, then you will also increase the amount of current generated. The last thing that you can do is take two magnetic bars, and also put it inside the coil to create a magnetic flux. And when you do this, you also see that this generates a larger current. So let's take a look at the direction of the current using the right-hand rule. In the right-hand rule, current is going to be represented by your thumb, and the magnetic field is going to be represented by your other fingers. So when you put the metal bar into the coil of wire, the magnetic field is going to be pointing this way, and the current is going to move in a counterclockwise direction. Likewise, when you take the magnetic bar out of the coil, then the magnetic field is going to be pointing this way, and the current is going to be flowing this way. So in this setup here, we have the power supply connected to the primary coil, and the secondary coil is connected to the galvanometer, and we have a switch. If we open and close the switch, this causes a change in current, which causes a change in magnetic flux in the secondary coil. And as you can see from the galvanometer, this generates current. Another thing that we can do is we place a metal bar in the setup here and repeat the same thing, opening and closing the switch. And as you see, that there's a larger amount of deflection, which means that there's a larger amount of current in the secondary coil. Okay, so let's do another demonstration. So in this demonstration, when you turn the switch on, there should be a flow of current through the solenoid. This creates a change in magnetic flux, which will generate a current flowing through this metal aluminum ring here. So when you turn the switch on, it should jump. Alright, so now let's do the same experiment, but this time let's use a metal aluminum ring, but this time it's going to have a slit. Now, what do you think is going to happen when we turn the switch on? Nothing happens. Why do you think this is so? Well, if you don't know, then I'll tell you. So this metal ring has a slit through it, which means that the flow can't continuously flow through the ring. That's why when you try to turn the switch on, it doesn't jump. So let's try the same experiment, but this time let's use a different sized ring. So if we do the same thing for this sized ring, and we see, you see that it goes much lower than this one. And why do you think this is so? Well, this ring has a smaller cross-sectional area, which means that there's less current flowing throughout the ring, and this is why it doesn't jump as high. Now also, if you take a light bulb and you put it through and you turn the switch on, you see that it glows brighter when you put it more towards the center, and then it's dimmer up here. This is because there's more current flowing lower down.